Okay, started. Oh, okay. Is my screen visible? I think so. Okay, so guys, I think you guys are first year or second year BTech or MTech students. I don't know. So basically, today we are going to talk about little bit about the quantum mechanics. So the quantum mechanics is it's a very tricky. If someone saying that I know the quantum mechanics, I think he or she probably the most what is called most bad person. You don't know about anything about the quantum mechanics. Whatever they are want to understand that the quantum mechanics, it's not very easy. So the famous guy who is called Feynman, he also saying that he don't know about the lots of quantum mechanics. Only he can do the only the mathematics. It's based on the mathematics. So coming from the first things from you guys, I think you guys are follow the all the lectures from the professor Anindra Datta. So in, in that lecture, I think he probably explained many things. Some of them in, let's suppose, in particle in one free particle in particle and particle in 1D box. The sub he supposed to uh, derive all those equations, and some of it is not derived by him. Uh, he's he gave that assignment to you to derive your own. So in that regards, do you have uh, any questions or any problems you are finding during your solving or any understanding? Please let me know. I'll take those questions first, and then I'll start the other uh, other problems to solve. Okay. Whoever there, please raise your hand and then ask us some questions if you have. You guys follow the lectures? Hello. It's always happens. I'm always talking to screen. Nobody actually answering or questioning anything. Okay. So if there is no question, let's start the things. It is what is my pen? Is it work? Okay. So now coming from the scratch, we started with the simple atomic model to how the atomic models comes in our scientific level. So he started with the Rutherford model, how the Rutherford model actually comes into the scientific world. So they started some experiment called alpha particle bombardment to the gold foil, and he found something called some uh, particle diffraction into that detecting screen, that is the photovoltaic sorry it is a photographic plate, how we are getting the x-ray. So we are we are passing through the X-ray through the that plate, and we are getting the image of that. So same, they found some. We have some. What is that? Your gold. This is the. Let's suppose we have the gold foil. uh, We have a gold foil. We have a alpha particle source over here. Let's suppose this is the alpha particle source, and we have a photographic plate over here surrounded this gold plate, and then it's bombarded to the direction. Some of the particle will completely reflect, and most of them are passed through with that gold plate. So, oh, sorry. Yes. So this phenomena actually coming because of this is the alpha particle. So this phenomena actually coming because of that this alpha particle is actually reflecting to a very heavy at heavy mass, and that actually make that reflection, and most of them alpha particle actually coming passing through that plate because of we have a atomic level where the most of the space are vacant, void space. So in that experiment he conclude that the atom having atomic structure is having a very centric one centric heavy mass into that atoms, and a very large void space in the atom. So that's why the most of the alpha particle passing through with that gold plate. So this is how he postulate initially, and then there is some other contradictory point coming out of it, that uh, that if, and he also said that the nucleus which is present into the atoms are centered into that atom, and then the electrons are circularly moving around my atoms. So if it is happening, so if circularly rotating into that in center of nucleus, then it's supposed to fall down into the nucleus, the electron, because of there is a electrostatic interaction between the nucleus positive charge and the electrons at the negative charge outer side of the my atoms, atomic orbitals. So after few seconds, after few picoseconds, this atom should collapse, but it is not happening. So from the starting with the Rutherford model is giving the idea that the the major mass of the atoms present into the nucleus, but and the in the electrons are in void space, but the distribution of the electron is not true. So in the Rutherford model, we have one point is that the uh, major mass are at nucleus, and and electrons are moving in the void space. Sorry. And third is that the flaws of this, the if electron is moving around uh, the orbitals in circularly after the electrostatic interaction, so these electrons fall down into the nucleus, so atom will collapse in a few picoseconds. So this is the flaws of Rutherford model. Now there is uh, another scientist called Bohr, Niels Bohr. They actually found some postulated some uh, found some experimental value that the atomic spectra of the any atoms, they are distinct in nature, and they have a line spectra, not a continuous spectrum. So that means this uh, the energy level, the line spectra means the spectra is coming from a energy absorption, and energy mainly from the energy absorption. So if there is some energy gap between some levels, the energy levels, they are absorbing some light, so we'll get the spectrum. So to finding that this kind of line, he postulate uh, one a, an energy level series, which is called this lambda. Lambda is the wavelength, will be R, Rydberg constant, and which is the energy transfer happening from the level, which level, this is 1 by n1 square minus 1 by n2 square, and this R value will be 1.09678 cross 10 to the power 7 meter inverse. So this equation you're supposed to remember while assigning your some assignments. There will be some questions based on this equation. So they will ask the in the Balmer series, they find the wavelength of the spectra where the energy jumps from the n level equals to something called nanometer level, which is nanometer level, and 410 nanometer to or 434 nanometer. So based on that, you can calculate the lambda value. Okay, now in the Bohr model, they introduced the angular momentum, the energy expression. In the Bohr model, energy expression will be energy expression something called m e to the 4 8 epsilon square h square dot 1 by n. So this is the energy expression. So the atomic spectra, whatever we are getting, so this atomic spectra coming from the absorption of energy from one level to another level to excite the my molecules, not molecules, excite the atoms. So that energy gap is always depends on the equation from where to where the transition happens, which is actually me e to the 4, which can be derived from this equation. This is n and this is the h. This is h means the Planck constant. So 8 epsilon square h square and in bracket it will be 1 by ni, the initial from where the transition started to from where the transition happened, which nf, which is actually h nu, whatever we are. H nu means whatever our spectral line we are getting, that is. which is actually energy. And here the n equals to 1, 2, 3, 4, etc. And from here, this Rydberg constant, there is this one, is coming from this equation. This equation is actually Rydberg constant. Applying all those values, that is the m mass of electron, charge of electron, epsilon value, and h square, will give you the value of this 1.09678 into 10 to the power minus 7 meter inverse. That actually you know in the your class 10 plus 2 level uh, yeah, textbooks, chemistry textbooks. Okay, now he told about the something called Zeeman effect. We have a atom. We are looking for the spectra. If we place this atom into the magnetic field, the spectral line actually increases. Why? Because we have a atomic orbital called n equals to n equals to uh, 1 to n. Then we have some orbitals called s, p, t, f, and the shape of these orbitals are something called like the spherical in s is the spherical in nature, is the uh, dumbbell like structure, d is that core system. Oh, sorry. No, 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 no. I'm sorry. Coming to the wrong direction. In the Bohr model, we found that energy transfer happening from the n equals to n level to n equals to n1 to n equals to n2 level. Let's suppose this n1 and n2 level have their, if you put in the magnetic field, they will give you that they give you the some splitting, because of, if you know that if electron is moving around a orbitals, it will create a charge particle. It always create a magnetic field. In that magnetic field actually affect your external magnetic field whichever you are providing into your experiment, and that gives you two angular momentum value, which is called, let's suppose we have a n equals to 1 value, then we have a angular momentum value. The magnetic field give you the another three angular momentum, which is called plus L, plus 1, 0, and minus 1. That's how we are getting the angular momentum, angular quantum number, which is called the uh, uh, plus minus L. Okay, and then here comes the first major equation for the quantum mechanics, is called Heisenberg uncertainty principle. Called actually Heisenberg uncertainty principle, which is which equation is that the uncertainty of the position and the uncertainty of the momentum is greater than h cross, greater or equals to h cross by h cross by 2. H cross nothing but h cross h by 2 pi. So in case you can write it as h by 4 5. So in Heisenberg principle, they are saying that we cannot measure the position and the momentum of a particle simultaneously. In a one particular time, we cannot measure the position and the momentum uh, in a simultaneously. So there should be some uncertainty. Okay, so interestingly, let's suppose we have a momentum distribution, something like, sorry, this is the axis, this is the x-axis, and this is the y-axis. Let's suppose our momentum uncertainty is something like this. If it is going sharp and sharp in nature, then my position more uncertainty should be broader in nature because of the because this position and the h delta h cross and the delta p cross is constant. So if delta p becomes sharp in nature, then my position will be broad in nature. I don't think you guys follows those uh, uncertainty of the distribution of the in Gaussian curve of this position or any momentum. It will come into your higher advanced quantum mechanics level. So this equation people always ask. We remember this is the Heisenberg uncertainty principle. It will come multiple times for solving the hydrogen atom problem. So now coming another equation. This is the postulate. It is not deriving from any equation. This is postulate. That's how in the Newton law, it is a postulate. Based on that Newton law, you can derive. In the Schrodinger equation, it is a postulate. Based on this, you can derive many equations. So in the Schrodinger equation, it is saying that the my one operator operates on in a function give us some eigenvalue and with function, and this is called eigenvalue equation. In mathematics, it is called eigenvalue equation. And in quantum mechanics, in mathematics, in what is that? In quantum mechanics, this equation known as Schrodinger equation. Okay. Now another another in this time there is a one uh, scientist called Albert Einstein. We all know about this. He told that the wave has a particle nature. Einstein says the wave has particle nature, which is coming from the photoelectric effect. Okay, and followed by de Broglie hypothesized that Another scientist called de Broglie hypothesized that particle also has wave nature, and this uh, wave has a particle nature. It will be denoted by h nu equals to uh, frequency h nu equals to energy. That means this energy coming from the particle term, and h nu is coming from your uh, the wave equation of the light. So this is wave nature, and then the wavelength of that uh, the wavelength of that particle wave nature is defined by h by p. P is the momentum, which is actually h by mv. This is a very important equation. You have to remember while people are asking having a particle, a wave, to determine the wavelength of the de Broglie particle, which is having the mass something which actually given to you, and also velocity of that particle also can be give to you, and then you can easily derive from that the from this equation, where you know that this value of the h equals is uh 3.626 into 10 to the power 34 joule second. Okay, so this is the equation. We have to remember this. Now our main quantum mechanical term is that Schrodinger equation. This is the first quantum mechanical equation. Based on this equation, we will derive lots of uh, lots of quantum mechanical problems. First of all, coming that equation, we have this Hamiltonian operator in quantum mechanics. We have some time dependent equations. For we'll separate out the time dependent part from the Cartesian part, and then we'll combine together in later on, and while you are using the time dependent perturbation. So the what is the someone will call the what is the time dependent Schrodinger equation? Fine. It is derived at IH cross del del T psi of x y z. This is the direction, and T, which is actually given by minus of h cross by 2m. Uh, this is the kinetic energy value operator, and this is actually kinetic value, and this is the potential energy value. Here the psi, the function, where it depends on the xyz plane as well as the time, and we have to separate it out by the some using some postulate. After separation, it will looks like your if psi is can be separate, psi x y z t can be say that psi of a x y z combination of two function. Sorry, this will be phi of n. This depends on only time, and from it we can separate uh, both the functions as ih cross phi t del phi t del t, which is equals to h cross square 2f psi of n x y z square, which is equals to some constant. This is called separation constant. And from it you can easily calculate what is the phi value, and from it you can say that ih cross phi t del phi t dt equals to w, and solving this equation it will give you yes phi t equals to e to the power minus I w t by h cross. And this equation we have to derive for many problems. So this is quite easy. We'll get the time dependent part, but position part is that depends on your xyz value, xyz plane position, and depends on your operator, which operator you are using. So in classical mechanics, this Hamiltonian operator is called H, is it depends. We are saying this is psi. This H actually represents the total energy. So we have to remember the Schrödinger equation, H psi equals to E psi, and it is the eigenvalue pair. Okay. So in why this is actually operator form. In whenever you are writing something called H or H psi, this is in classical, this becomes the operator. So whenever you are addressing some operator, you're supposed to write a hat on on some operator. Now here comes some postulate of the quantum mechanics. So the quantum mechanics, there is some operator which is the position operator. That is actually X operator. Second is the momentum operator. Which is called Px as the X direction is H cross by I and d dx equals to minus IH cross ddx. And then we have kinetic energy operator, which is actually denoted as t in x direction minus h cross by 2m d2 by dx square. Okay. And the potential energy operator is the v of x. Okay. Then this law again saying something that we have to follow. This postulate, this is the one. Two is that the operator of the eigenfunction gives the eigenvalue, and that eigenvalue, those are can be operator, the appropriate operator of eigenvalue eigenfunction gives the eigenvalue, and that eigenvalue should be real. Three, the quantum operator should be linear. What does it mean? quantum operator should be real, should be linear. Sorry, what does it mean? That means we have a operator A who is actually function of the some constant of the phi 1 c1 phi 1 plus c2 phi 2 will give us c1 minus phi 1 plus c2 operator A phi 2. This is the uh, this should follow for a quantum operator. Fourth, another is that the eigenfunction of quantum mechanical operator are orthogonal to each other. All the eigenfunctions of quantum mechanical operator are orthogonal okay. It doesn't mean what it is mean. Minus this is integration plus infinity to minus infinity. This is called psi star x. And the psi n x dx equals to, which is can be denoted as bracket notation, should be 0 orthogonal as it is orthogonal. And another is that the wave function should be normalizable. Another, we have to calculate something called probability density, which is denoted as the psi of xt, which is called probability density. And another term is average value, which is denoted as some operator x, which is denoted as suppose minus infinity to plus infinity x operate on something function v of x dx is this is the called average value. Everything will get the plus note, and which is provided by the professor. Now coming question is that which will be the acceptable wave function. Acceptable That function should be normalized or normalizable. Second is that the function should be continuous. And third is that psi dq, the first derivative of that function, that also be continuous. And that will give you a, if you operates that after operation by a operator, give you a single valued eigenvalue. After operation will give you, it will give single eigen value. Okay, so sometimes you have to note that sometimes we need to give the boundary condition required to accept the wave function. Okay, so this is the four uh, fundamental laws of the which will be the acceptable wave function for quantum mechanics. So there is some, let's suppose with some example, we have a function called, this is some function, this is some value is, so this function, some function uh, is like this function is not continuous, not continuous. So it is not acceptable, then not continuous, that means not acceptable. Then let's suppose another function is having multiple values in a one particular, yes, in that, let's suppose we have in this x direction we have a multiple 1 2 3 value, that means this is also not single value function, not single value function. So this all also not acceptable. Okay, Now, coming to a first problem, which is called free particle. Okay, what does it mean, free particle? We have a particle. Suppose we have a particle, it can move both the direction to infinity, plus infinity to minus infinity. So how we can solve this equation? As it is free particle, as it is free particle, so it has the potential energy to 0. That means my v x, and that is if free particle in one direction, v equals to 0, vx equals to 0. Now my Hamiltonian operator, that is combined of h, which is combination of potential energy and kinetic energy operator, which is called h cross by 2m d2 by dx square of of psi of x equals to e of psi x. Now we can take a trial equation. First of all, we'll take the one, second one will I also take, and we'll try to solve those equations. So first of all, this psi x can be written as a function a something constant a of sine k x plus b cos kx. Okay, so how what will be d psi dx? It will be a k cos kx minus bk cos sine kx. That implies again second derivative, first derivative second derivative will give us of d2 by dx square psi of x, which is actually a k square minus minus a k square sine kx minus b k square cos kx. Okay, if you take the k square out, minus k square out, will give a sine kx plus b cos kx, which is, that means That means minus k square psi x. So my operator looks like, how it looks like. Now you can say that d square psi x by dx square is to minus k square psi x. If we multiply both the side with minus 2h cross by m, h cross by 2m. D square psi x equals to h by 2m minus k psi x. That means this one is that known as e of psi x, which is equals to minus, oh, that means minus is the plus hk by 2m psi of x. Oh, this is k square. So we can say from here, we can say E equals to h cross a square by 2m. So this is the energy equation, and from here we can calculate the k value. K equals to 2 m E by h cross square root of, this is the equation of k. Now this is a trial equation. Let's suppose we have another trial equation. This is called psi of x equals to c into the power I kx plus d into the power minus I kx. Okay, so this is the equation. We will try to solve it. Before that, we can say the psi equation of psi x should be, what is that? We know the k value. So the equation should be, looks like 2a, and this will be the plus minus, sorry, a sine root over of 2m e by h cross x plus b cos 2m e by h cross x. This is the equation. Now we are trying to solve this equation, taking a trial equation of psi Okay, so in the next page, our psi equals to e to the power, acha, c, c into e to the power minus I kx plus d into e to the power minus I kx. Now d, similarly d psi by dx will give you minus I k c into e to the power 1 minus I kx minus of d I k e to the power x. Now again second derivative d2 psi minus of sorry it will be I square k square I into k whole square c e to the power I kx, and it will be minus of minus, that is plus, and it will come another I negative I, so it will be minus actually. It will I k whole square d, so minus 1. So I square k equals to minus plus minus ik minus k square c to the power ikx. This will be minus k square t to the power minus ikx. Okay. Here are matches for dkx. Take minus k square out, will give c to the power ikx minus k square d to the power minus ikx. It's which is minus k square again psi x. So that does mean E equals to 2m equals to h cross k square by 2m. Same coming into that the initial equation, whatever we do, and then again also k square value by k equals to plus minus root over of 2m e by 2m e by is that 2m e by h cross. Now, how will be the function? So my function is psi of x e to the power c into e to the power minus e to the power, sorry, e to the power ikx plus d to the power minus ikx. You can write this e to the power ikx can be write as cos of kx plus I sin x, and this one can be write as c c this one d cos kx minus d cos sin x. Okay, now c and d first, then it will give you cos kx plus cos no, this is not the correct way to solve this. From this equation, you can another operator you can operate on this psi value. It's called, we know that h cross by I d by dx e to the power ikx, which is actually give you h cross k by I into e to the power ikx. So that means this is the momentum equation, and this is give you the p cross psi will give you h cross k by I of psi. This is the equation you can get. Now, now the major problem is arising, which called is called the restriction. So here we don't have the no restriction. As you can see, this k can be n number. There is no restriction on k. Second thing is that e can be any value. At 3, no quantization. What does it mean? Quantization means the each particular it cannot be the whole function cannot be quantized. So now here comes the particle in a 1D box. So what it is there. So we can restrict the particle in a particular value. This is, let's suppose L equals to 0 to L equals to 1. We have a particle. In here, we can say that see, in that region, we can say that particle has a B equals to here, the potential energy equals to 0. Okay, and while it tends to the L, it becomes infinity, and whenever the particle tends to 0, it will become the potential energy will be the uh, will be infinity. So coming into this into a accounting this into a picture, we have a equation, eigenvalue equation, where my my energy equation is H previously whatever we got, which is k square by 2m, and applying the boundary equation, that means psi of x greater than 0 to 0 and x less than, and psi of x less than L equals to 0. With the boundary condition applying, we have a function is called a sine x So what will be the average value? It will be 0 to L psi square this should be proposed. And this is the normalization factor. That means 1 by a square 1 by 2 0 to L 1 minus 2 cos 2n pi by Lx dx. That means we will that half 0 to L dx minus of 0 to L cos 2n pi by Lx dx. So from here a equals to root over 2 by L and psi of x equals to root over 2 by L sine of n pi L, right? N pi L. Okay, so now coming another interesting part, which is called node. So if my equation is psi equation equals to root over 2 by L sine of n pi by L x, where n equals to 1, 2, 3, dot, 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 dot. Depending on that, how will be my energy equation? So energy will be a distribution for the n equals to 1 to n. So it will looks like my function is like first one, it will give only this. Second one give me while n equals to 2, it will give the function distribution like this. Third one will give sorry, my drawing, this will be like this. So where n equals to 1, n equals to 2, n equals to 3, and so on and so forth. We have a further so on and so forth. So here you can see here the some point in between 0 to L. There is some point except the n equals to 1. There is the function value has 0, which is this is called node. Here also we have the 2 node over here. Okay, so that's how the node actually coming into the picture. So now we have the orthogonality. That means we have a psi1, psi2, sorry, psi2, psi1 should be 0. So how we can say, if we have the value multiplying this function to this function, we have the value till this point, we have a positive value like this, and then we are adding up, this is the negative value we have, and that means all cancel to each other and becomes 0. So we have that means we have a summation of x equals to 0 to L psi 1 x psi 2 x. So all, if I sum up everything, that becomes the multiplied of two functions, it will give the 0 value. So that means my here the psi of x over 2 by L sine n pi by L x is the orthogonal, and it is continuous. It is also continuous in between the 0 to L, and that means it can be it is also acceptable, and further first derivative of psi also a continuous, and it giving the one particular energy value for one particular rate. That means it is a single valued function, single eigenvalued function. So that means this psi x is acceptable wave function. Okay, so that you can calculate. Interestingly, now we have to calculate some node of 2D function. How it will looks like? We have a one function over here, which is have a nodes finding of combination of rectangular nodes finding in rectangular box. 2D box. So we have a rectangular 2D box. We have a box something like this. We have a y equals to x equals to 1 and y equals to 2. That means our function looks like, in the first case, y equals to 2, here y equals to 2, and we have another function here, x direction. This is the x equals to 1. So our node, how node should be, and node should be, this will be is positive, and this node should be here and negative. So that means this is the rectangular 2D box where we are finding the nodes where the x equals to 1 and y equals to 2. It looks here the positive lobe, here is the negative lobe. So that's how we can find all those nodes in the for multiple 2D multiple 2D degenerate or non-degenerate states. Okay, so then professor also covered other things, that is that how to change into uh, the Cartesian coordinate to r r theta phi, and depending on that you can transfer xyz into r theta phi in the angular position as well as in the distance from the origin. So I think he is covering other things. So till this, I'm stopping here. We don't. I don't think nobody is here. So I think everyone left. Next day onwards, we'll try to solve lots of questions. And I will request you to ask question. Otherwise, it's very difficult to me know the problem whatever you are facing. So this is how I got that know what to let you know that this much part is important for knowing this quantum mechanics, and based on this you have to solve lots of problem in future. So from it I can stop it here, and if you guys don't have any other questions, so I don't think. Okay, then it's fine, stop it here, and then next day we'll continue with the hydrogen atom problem. Thank you.